Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be going through the AQA A-Level Chemistry Paper 1 from June 2018, so let's get started. So this question's about lattice enthalpies. Figure 1 shows a bond cycle for the formation of magnesium oxide. Complete figure 1 by writing the missing symbols of the appropriate energy levels. So you guys know this by now if you've watched my other videos. There's only one way to do all of this topic, and it's to know what these definitions are and to turn them into equations so you can compare line by line as well. There is no other way of doing any enthalpy stuff. You have to draw a cycle every time. If you're doing like an enthalpy of hydration or a solution or whatever, you're going to draw. You've got to draw a Hess's law cycle. All of this is just Hess's law, but on like steroids. So anyway, here, the missing arrows are what? So let's have a look what we've got so far. So we've got magnesium solid plus a half O2 gas gives you magnesium solid plus O gas. So that's the enthalpy of atomization of oxygen. You should be able to recognize it straight away. Magnesium solid to magnesium gas. This has changed. Atomization of magnesium. Then for some reason, we've got something, 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 something. And then eventually you end up with magnesium 2 plus and O2 minus. So what must be the next line is that magnesium gas has become plus O gas plus E minus, as in the first ionization energy. And then magnesium 2 plus gas plus O gas plus 2E minus, which is your second ionization energy, right? And then we've got Mg2 plus gas plus O gas minus plus E minus. That's your first electron affinity, second electron affinity, and then you've got all these stuff there. Then it says, calculate a value for the enthalpy of lattice formation. So lattice formation is where you're going from gaseous science to a solid ionic lattice, right? So go through and just label all of these and look what's happening. Hess's law says if you start and finish at the same point, it doesn't matter what route you take, it's the same. So if we start and finish here, then that means this is the enthalpy change, and that's the same as going all the way around this way. So what I do is I just write the arrows on the thing. So we're going from solid magnesium and half O2 gas, so they're in the elements in their standard state, so we're making a solid ionic compound. That is going to be the enthalpy of formation for this, which is minus 602. Cool. Then we're atomizing the oxygen. So if we atomize oxygen, that's going to be here, right? But then if you see it says bond dissociation enthalpy of oxygen, which is where you're breaking 1 mole of a bond over a blah, 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 whatever, right? That's going to break it down into, anyway. So it's actually this one here then instead of the atomization of atomization energy. So it's going to be 496. Then from here to here, it's atomization of magnesium, which is going to be 150. And then from here to here, it's the first ionization of magnesium, so it's 736. Then it's the second ionization energy of magnesium, which is 1450. And then we've got the first electron affinity for oxygen, where are you, which is here, minus 142. And then the second one, we've got plus 844. And then this is the missing thing we want. So this enthalpy change here is going to equal all that's around. So I can say that minus 602 equals 496 plus 150 plus 736 plus 145 plus 1450 plus, minus, should be a clear minus, that's right, minus 142 plus 844 plus the missing enthalpy change we're looking for. Just a little thing that I've realized I slipped up on, whoops, is that the bond enthalpy is where you break 1 mole of bonds, right, to get gaseous atoms. But the thing is here is that you've got a half O2, so it's actually a half 496. The reason being is because you have that and you're breaking 1 mole of it, and that's one of those, right? But it's a half O2, so you've actually got half of what that would have been. So in this case, wherever the 496 is actually a half of it there instead. So then if I work this out, let's see what we get. So minus 602 equals, we get 3286 plus delta H lattice enthalpy. So delta H lattice enthalpy is going to equal this minus 602 minus that. So minus, that gives us minus 3888 kilojoules per mole. Let's try and match the significant figures in the question. So minus 3890. So nitrogen and hydrogen are mixed in a 1 to 3 mole ratio and left to reach equilibrium at this temperature. And the equation for this is shown below. When equilibrium was reached, the total pressure was this, and the mole fraction of that was that. So let's calculate the partial pressure of each thing here. They've told us that equilibrium, this is the mole fraction, right, of the NH3. So 0.80 is the mole fraction of NH3. So partial pressure of anything is its mole fraction times the total, right? All of these need to add up to the total pressure. So then if I can work out how much NH3 there is by just doing 0.8 times 150, right? Which means I've got 120 kilopascals of NH3 already. So that's going to be 120. So then the amount that's left, the N2 and the H2, must be 30 kilopascals. And that's shared between them in a 3-to-1 ratio. So, 1 to 3 ratio. So that means that this is going to get, so you do 30 divided by 4, which is going to be what? 30 over 4, which is 7.5. So there's going to be 7.5 N2s, and there's going to be 22.5 of the others. 7.5 and 22.5. There you go. Then it says write the equilibrium constant Kb for this. So it's just going to be it's partial pressures of all of this instead of concentrations. It's going to be partial pressure of NH3 all squared all over the partial pressure of N2 times the partial pressure of H2 all cubed. Then it says in a different equilibrium, make sure the partial pressures of these are shown. Calculate the value of the equilibrium constant K. Just plug it into the other one there. So I'm just going to zoom out so I can actually see it. It's going to be Kp is going to be 1.1 times 10 to the 3 squared all over 1.5 to 10 to the 2 cubed, sorry. And that's going to be 1.22. If I do that and I plug that in, I get 0.0029. So 0.0029 is what Kp is. And if you look at our units, what's the question given us in kilopascals? It's kilopascals squared all over something cubed, so it's going to be kilopascals to the 4. So 2 minus 4 is minus 2, so it'll be kilopascals to the minus 2. There you go. Now it says the enthalpy change for this reaction is minus 92. State an effect of the increase in temperature on the value of Kb for this reaction and justify your answer. So anytime you make a change to an equilibrium, the equilibrium will shift to counteract the change. So if we increase the temperature, is what the equilibrium shifts to decrease the temperature. So I always like saying that because then I know what I'm looking. I've already dealt with that mark earlier, right? A lot of people like to say increase the temperature, it moves to the other side, blah, 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 but they don't actually say why. I'm saying here, if you increase the temperature, the equilibrium shifts to counteract the change. And I'm saying it there. Like, you don't just say counteract change, you need to say what it is. In this case, if the forward reaction is exothermic, then it means it's going to shift to the left. In this case, shifts to the left. So I'm saying shift to counteract the change. How by shifting to the left? In the endothermic direction. So what that means is you're going to have less product, right? Which means you're going to have a smaller Kp. There you go. The only thing that affects Kp, Kc, Ka, anything is temperature, though. All the rest of them just balance out to sort of, if the products go up and the reactants go down and so forth, whatever, right? But the only one that changes it is temperature. Everything else, nothing. The only factor that changes is temperature, nothing else. So here it says calculate the entropy change for this reaction between ammonia and oxygen. So what you do is you do delta S equals S end minus S start. So the S at the end is going to be 4 lots. So that's going to be 4 times the NO, which is going to be 211, plus the 6 times the H2O, 189, minus the start one. So it's going to be minus 4 lots of the 193, minus the 5 lots of the. If we do that, we should get plus 181 joules per Kelvin per mole. Then it says calculate the free energy change, Gibbs free energy for this when it's at this temperature. And if you're unable to obtain this, blah, blah. Okay, right. So delta G equals delta H minus T delta S. In the question, they've told us this is delta H, so it's going to be minus 905 minus the temperature, which they told us is 600, but we need to convert it to Kelvin. So you add 273, so that's going to be 873 times delta S, but this is in joules per Kelvin per mole. We need it in kilojoules, so I'm going to divide it by 1,000, so 0.181. If I do that, we should get minus 1063 kilojoules per mole. The reaction between ammonia and oxygen is carried out at high temperature. What happens to delta G as this happens? So delta G equals delta H delta S, right? So delta H is negative, delta minus T, but then delta S was positive. So then if you look at it in one big chunk, this is always a negative value minus a negative value. So that means if I increase this temperature, this whole chunk is going to be more and more negative. That's also negative. So doing a negative and another negative, right? That minus them. So that means even more negative. So that means what happens is delta G is more negative. Why? Because T delta S gets bigger. It says platinum acts as a heterogeneous catalyst in the reaction between ammonia and oxygen, so it provides an alternate reaction route and lower activation energy. Describe the stages of it. So here, it's told you it's heterogeneous, so platinum is just sitting here. We want the ammonia and the oxygen to do something. Every single reaction in the universe depends on collisions and also an interactivation energy. So loads of people started yapping about saying, it provides an alternate reaction pathway. That's not what they want to hear. They literally tell you acts as a catalyst, bro. And it literally tells you that it's an activation energy that's lower. It's asking you by doing what? These are whizzing around. We need them to collide with each other. We need to get their activation energy. So maybe, and we got this solid pattern, and perhaps they stick here and then they actually collide like that by touching each other like this. So that's dealing with the collision spot, and maybe it lowers the activation energy by doing that. So then they react because it, forces them to hold together, and then they detach as one product. And that's exactly what happens. That's how they work. So that's what you would say. The reactants adsorb, not absorb. Absorb means go into, adsorb means stick to the platinum surface. And then what happens is that the reaction happens, right? Whenever you're doing reactions, you're breaking bonds and then reforming them. So then it means bond breaking and making, or the reaction, happens on its surface. And this lowers the activation energy. And then what do they do? They detach, they desorb. So you get desorption of the product. There you go. Right, so the next question says, deduce the change in oxidation state when NH3 is oxidized to NO. So it's told you in there that it's been oxidized as well, which is a hint. But if we look here, the nitrogen is, well, so that's going to be -2, so it's going to be +2. And here, that's +3, so it's going to be -3. So you can see it's gone from -3 to +2, so that's been oxidized. -3 to +2. When ammonia reacts with oxygen, nitrous oxide can be produced instead of NO. Give an equation for this. So it's told, so always start with what you know in the equation. So they've told you it's ammonia and oxygen. Make an N2O. Now here, you're sticking oxygen onto the ammonia, but the hydrogen's not been dealt with, so probably going to make H2O as well, considering we're reacting with water. So then, let's have a look. We've got N2 here, so we put 2 there. There's 3 H2Os there, so we could put 2 NH3s here, which is 6, sorry, and then that's going to be 3 H2Os, and then how many waters do we need? 1, 2, so 2. There you go. That's how you do it. So here it says this question is about S block elements. Give the full electron configuration for the calcium ion Ca2+. If you look at our periodic table, that's our S block. So we know it's in the S block because here it is. This is period 1, period 2, period 3, period 4. So now it's going to be 4s2 is its original, right? However, it's the Ca2 plus ion, which means its outermost electrons, which are in 4s2, are gone. So that means it's going to be all the way up to 3p6. So 1s2, 2s2, 2p6, 3s2, 3p6. There you go. Now it says explain why the second ionization energy of calcium is lower than the second ionization energy of potassium. So if we look back here, second ionization energy is you're taking out the second outermost electron. So Ca2 versus K. If you think about it, we're peeling this out of an S1 and then an S2, right? So they're both in the same period. So they're both going to be 4s2, 4s1. The only difference is that when you're pulling out of when you're pulling the electron out of this 4s, so the first ionization energy is going to be 4s1, the electron's been removed from. Then you're going to go back into the next one, so 3p6 and then 3p5. Whereas here, you're taking all of them out from the 4s2. The only difference fundamentally between the electrons you're taking out is that for calcium, you're taking them out of a 4s2 versus a 3p6 and 4s1, which means you're taking it from a higher energy orbital. So comparing them side by side, the only difference is that Ca2 plus, its outer electron is further from the nucleus, and Ca2 plus loses electrons from higher energy orbital. And as well as that, we're in 4s2 versus 3. So as well as that, there's because of the higher energy orbital as well versus the 3p, was going up into a new subshell as well. So there's more shielding as well. Because in K plus, you're going back down into 3p, whereas Ca plus, you've still got 4s1 left, like I said above. Identify the S block metal that has the highest first ionization energy. So it's an S block metal, and it's going to have the ionization energy is where you're taking the outermost electron away from it. It's got to be one of the smallest ones. So it's between these two. Now, between lithium and beryllium, this one has got one extra proton and one extra electron. So it's going to be beryllium because that one extra proton actually increases the attraction between it and its outermost electron. These two are already too big. So therefore, it's beryllium. Give the formula of the hydroxide of the element in group 2 from Mg to Ba that is least soluble. So it's magnesium hydroxide is the least soluble. As you go down the group, the hydroxides get more soluble, but as you go down the group, the sulfates get less soluble. The student added 6 centimeters cubed of barium chloride to 8 centimeters cubed sodium sulfate, and then they filtered out the precipitate and collected a ionic equation for the formula of the precipitate. And it says, show by calculation which is in excess, and then calculate the total volume of the other reagent that should have been used if the filtrate contains only one solute. So if we have a look at the ionic equation, what are we reacting? So we're reacting barium chloride with sodium sulfate. So whenever you're adding a barium something to something sulfate, it's going to make barium sulfate. So off the bat, I know we're making barium sulfate solid. The ions that are making this are going to be Ba2 plus aqueous plus SO4 2 minus aqueous. So we've done that part. Now it says, show by calculation which is in excess. All you got to do is work out the moles of each thing. So the moles of BaCl2 is going to be 6 over 1,000 times 0.25, which is 1.53 times 10 to the minus 3. And the moles of the Na2SO4 is 8 over 1,000 times 0.15, which is 1.2 times 10 to the minus 3. So then you can see that there's more of this, so BaCl2 is in excess. So then it says now total volume of the other reagent. So moles of BaCl2 are going to equal its concentration times the volumes at 6 over 1,000 times 0.25, which is going to be 1.5 times 10 to the minus 3. And then the moles of the Na2SO4 is going to be 8 over 1,000 times 0.15, which is 10 to the minus 3. So the BaCl, you can see is more of it, so the BaCl2, is that. So then it says, what's the total volume of the other reagent? We're going to need to get one solute, so it's going to be So it's asking how much of this is going to, how much can you use to perfectly react to both of them. So in order to have the Na2SO4, we've got to match the number of moles of the Na2SO4. So if we do that, now you're going to work out your volume using moles over concentration instead of, concentration goes moles over volume. And that gives you a new volume of, well, we're going to put 1.5 times 10 to the minus 3, the moles we want to get, the BaCl2 to react, over 0.15. If we do that, we get 0.01 decimeters cubed. If you convert that to centimeters cubed, that is 10 cm cubed. So sample strontium has this relative atomic mass, and it's got these three isotopes, and the ratio of these abundances of these isotopes is that. State why the isotopes of strontium have similar chemical properties, and then calculate the percentage abundance of the 88 isotope in this. So first of all, straight away, why they have similar chemical properties is because they have the same electronic configuration. The electronic configuration determines the chemical properties, what you would do in a chemical reaction, whereas the number of protons determines what element it is, and then as well as that, the number of neutrons determines physical properties as well. So same electronic configuration. So he wants us to find the 88 SR isotope. All we know is that its relative atomic mass is 87.7, which is going to equal all your abundances times the masses divided by the total, right? So what I'm going to do is I'm going to have a look and decide, I'm going to call one of them X and the other ones, right? So we've got, in this sample, 86, 87, 88. So when you're in a scenario where you don't know which one's which, like you've been given an unknown, just call one of them X using the facts they've told you. They've told you that 86 and 87 are in a 1-to-1 ratio, meaning that I could call these two X, right? Percent. If that's the case, then whatever's left over has to be what 88 is, which is 100% minus 2x, because that's what's left over. So then I can write 87.7 equals 86x plus 87x plus 88, 100 minus 2x over 100. Then if I rearrange this, I'll get 8770 equals 86 plus 87x plus, and then 8800 minus 176x. If I tidy this up, I will get 8770 equals 8800 minus 3x. So then 8770 minus 8800 is going to be minus 30 equals minus 3x. So x equals 10, right? But that's only the percentage of it, because the question wants you to find out the 88 SR isotope, which we said was 100 minus 2x. So we're not just done yet. That means the 88 one, abundance, is going to be 100 minus 2 lots of 10, which is 80%. There you go. Now it says this ion travels through a flight tube with a time of flight mass spectrometer with a kinetic energy of this, and the ion takes this much time to reach the detector. Here's your half mv squared formula, and they've told you that m is the mass in kilograms and v is the mass in meters squared, so the velocity or speed. The Avogadro constant is here. Calculate the length of the flight tube in meters and give your answer to an appropriate number of significant figures. So we know that speed equals distance over time. The distance they're covering is the length of the flight tube. So we're going to have to find out what v is to eventually get all of these, the distance here, because distance equals speed times time. Fine. So what you need to do is look at what you've been given in the question and start working with that. So we know the time it's taken to move. We know its kinetic energy, and we know the Avogadro constant too. Ke equals a half mv squared. So 2ke divided by m equals v squared. So v equals the square root of 2ke over m. Now the problem is that the mass, oh no, we don't have the mass. Except we do. The entire periodic table, the masses are always in grams per mole. So that's about 137 grams per mole, right? Or mole minus 1. Whenever you see that, it means that 1 mole weighs this much. So if I have 1 mole of carbon, it will weigh 12 grams. That's why it's 12. So they've only got 1 ion, though, which is what people don't realize, that this question's testing on an ion, not a mole of these. If I have 1 singular ion, it is not weighing 137 grams, because that's how much a mole weighs. To work out the mass of one of them, it would be this divided by how many is in a mole, Avogadro's number. If I have a mole of bananas, I've got 6.022 times 10 to the 23 in bananas. So do you know its mass? Its mass is going to be 137 divided by Avogadro's constant. So that's going to equal 2.275 times 10 to the minus 22. But we want it that's in grams, so we want it in kilograms. So it's 2.275 times 10 to the minus 25 kilograms. Then v equals the square root of 2k of m, so it's going to be 2 times 3.65 times 10 to the minus 16 over its mass, which we just worked out, is 2.275 times 10 to the minus 25. If we do that, we get 56646, right? And that's meters per second. Then we know that the question's told us Well, no, not the questions are there. Sorry, we know that distance equals speed times time, which is going to be your answer, times the time it took, which was what? 2.71 times 10 to the minus 5. If we do that, we get 1.535, which is roughly 1.54 meters. There you go. So state the meaning of a strong acid. So just completely dissociates in solution. Next, it says, in an experiment, this much hydrochloric acid was added to this much barium hydroxide. Calculate the pH that forms, and then here's Kw, and give your answer to 2 decimal places. So with any acids-base question, what I always do is I write HA, which is your acid, plus OH minus, which is your base, makes A minus, which is a salt, and then H2O, which is just, water, right? We don't really care about that in most cases. I use this to visually see what I have and then what I can use to, which formula I can use to eventually find the pH by finding H plus, right? So we're going to link back to this somehow. So what I do is I write the initial moles, N moles, and then N concentration, and then I have to look for all the pieces for the acid. So the acid's moles is going to be this concentration, the volume times its concentration, right? So it's going to be this over 1,000 times that. So if I do that, I get this many moles. So 1.035 times 10 to the minus 3 moles of this acid. Cool. Now with the OH minus, that doesn't mean you just dive into doing this. I need to find out how many OH minuses we get. This is BaOH2, which dissociates into Ba2 plus and 2 OH minus. So whatever the moles of this is, it's actually double that. So the moles of BaOH2 is going to be 25 over 1,000 times 0.15. Now if I do that, I get 25 over 1,000 times 0.15, which is 3.75 times 10 to the minus 3. But I don't want the BaOH. I want the OH minus, which is 2 lots of them. So I'm going to do 2 times that, which is 7.5 times 10 to the minus 3. So that's actually how many OH minuses I have. 7.5 times 10 to the minus 3. At the very start, when no reactions happen, there's none of that, and there's no water either. So then at the end, well, let's see, there's more of this than there is this. At the end, all of this will have reacted, and then whatever's left over is left over. So if that's gone down by 1.035 times 10 to the minus 3, then this will have dropped by 1.035 times 10 to the minus 3. So 1.035 times 10 to the minus 3 means that we've got 6.465 times 10 to the minus 3 moles of this. Now, the reason I do this is because I'm thinking logically, these are going to react with each other and decrease in numbers. So I now know that there's excess OH minus. Now, in terms of the A minus, yes, we're going to make 1.035 times 10 to the minus 3 and some amount of water, but I don't know any Kas, Kws, K anything that has OH in it and A minus in it. The only thing that I know that has OH in it is Kw, which I've also given you in the question. So that helps me guide what I'm going to do. So I'm going to be using the OH equation, the OH concentration in Kw. So then what I need to do is I need to work out the N concentration, which can be 6.456 times 456 times 10 to the minus 3 divided by the new volume, because we mixed 2 solutions together, which is going to be this plus this over 1,000. So 10.35 plus 25 all divided by 1,000. If we do that, we get a new concentration of 0.182885. Now Kw equals H plus times OH minus. So that means that Kw over H plus, over OH minus, equals H plus. So if we move here, H plus is going to equal Kw in the question, which they told us was 1.47 times 10 to the minus 14, over RH minus, which you just worked out, is 0.18, blah, 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 blah. If we do that, we get an H plus of 8.0378 times 10 to the minus 14. So pH is negative log to the base 10 of the answer, which is going to just be 13.09. So that's what I do, because then it means I can just sort of piece together like exactly what I'm going to find, rather than just sort of trying to look at it and visualize it. Like, it just helps me understand what I'm doing, because for some scenarios, you might add loads of acid to a base, and then you've got a mixture of an acid and its salt, which is a weak acid and its salt. For example, if we used a weak acid, and that means I can figure out that it's a buffer and do the next steps. So this just always helps me work out, which way I'm going down. So it says here, the pH of water is this. Give the reason why water is neutral in its temperature. So it's only to do with the fact that this is pure water, and in pure water, H plus equals OH minus. That's all. If they're equal, then you've got a neutral solution. So now it says, identify the oxide that can react with water to form a pH of 2. So it's anything that's a strong acid, which is this. All the rest of them don't really, and SiO2 doesn't, so that's... So now it says, give an expression for the acid dissociation constant for methanoic acid. So Ka equals H plus A minus, which is going to be CH3COO minus, because that's lost, the H over HA, which is going to be CH3COOH. Cool. A buffer solution contains this much sodium ethanoate dissolved in this much ethanoic acid. A sample of this hydrochloric acid is added to the buffer. Calculate the pH of the solution that's formed. So what I like to do is I like to just visualize what's going to happen in this. So we have our nice buffer of HA going to H plus and A minus, right? Now if we're adding HCl, what we're adding is we're adding H plus. The H plus is going to do something. What it's going to do, because all buffers hinge on an equilibrium, remember that if you make a change to an equilibrium, it will move to counteract the change. So if I'm adding H pluses to it, it's going to move to try and decrease the H pluses, meaning we're going to go that way, right? So if you think about it like that, then you can figure out the rest. And it's the same as every other thing in the universe, where you do your initial moles, then your end moles, and then your end concentration, right? So initially we have how much HA. So they've told us this is the volume and the concentration. So we can find the moles of the acid by doing 500 over 1,000 times 0.07. If I do that, I get 0.035 moles, right? Initially. And then the H plus, we don't know. And how much A minus do we have? We know that our sodium ethanoate is going to be 0.025 moles, right? In this much solution. And then the sample of solution has this much HCl added to it. So initially they're adding this much HCl and this much. So we're going to work out the moles of HCl and then hence the moles of the H plus added, right? So the moles of H plus added is going to be 5 over 1,000. So 5 over 1,000 times 2, which is going to be 0.01. So in this case, 0.01 has been added into this of moles of H plus. So then at the end, we know that the equilibrium will shift to bring it back down to normal. So it's going to be 0 and everything else is going to shift around. So if that's dropped by 0.01, this should have also dropped by 0.01 because we're going that way. So if that's the case, then the n moles of A minus is going to be 0.015. And then here, this will have gone up by 0.01. So that's 0.045 because that makes sense. If this drops as well because these two react together to make that. It's thinking about what actually happens logically in this equilibrium. Then we need to find out the concentrations because Ka equals H plus A minus over H plus A minus over HA, which is the concentrations of everything. So the end concentration here is we've got a new volume of 505. I think so. Yeah, 505. So our new concentrations are going to be 0.045 over 505 over 1,000, which is going to be 0.089109. And then here, that's obviously 0, but not necessarily 0, because remember, there was already some H plus to begin with. We just added some, and I'm just showing that it's going back down to the equilibrium amount, the normal amount the buffer has. And then the other concentration is going to be 0.015, which is going to be 0.0297, right? Now we know that Ka equals H plus A minus over HA. We're using this one because there's A minus in it, and A minus is from the salt. Whenever you say A minus in this, it's salt, because normally an acid is so far to the left there's barely any of it, so those two are equal. But in this case, because there's salt here, it's now got to be factored in, basically. So then Ka times HA over A minus equals H plus. So if we now put the numbers in, H plus is going to equal Ka, which was what? 1.76 times 10 to the minus 5, times the HA, which we just worked out. After this stuff's been done, so 0.089109, all over the A minus, which is 0.0297. Our new H plus is going to equal 5.281 times 10 to the minus 5. So then the pH is just negative log to the base 10 of your answer. And if I do that, we end up getting 4.277, which is roughly 4.28, because 2 decimal places. So again, any acids and bases question, if you just think about it logically like this, it makes a lot more sense. Whenever you set up a buffer, you have this equilibrium in these two. And I know initially I've added one extra 0.01 moles into this. I know technically it's not 0, but I know it's dropped down by this much to have gone back to its equilibrium amounts. So that means this will have dropped and this will have gone up. So we need to factor in all of those changes and then find out the new H plus A minus and stuff, and then use that. So students set up this cell in figure 2, and it says they record an initial voltage at that. Explain how the salt bridge provides an electrical connection. So whenever you're drawing any circuit in the universe, just a bit of throwback to physics, you've got to have like a sort of loop of current going around, right? So it's got to be a charge flowing. And if we have this without the salt bridge, then electrons are free to move like this, but then that's just about it. There's no extra movement of charge to keep the circuit working. It's not complete. So what we do is we add a salt bridge. Now that doesn't mean the electrons are moving across this. It just has ions in its own, like, K and NO3, K plus and NO3 minus, and they can move whenever to sort of complete the movement of charge. That's how these things work. It's charge. So in this case, it has ions that can move. That's why it allows those connections, the electrical connection to happen. The electrons do not move through these. Do not think that, though. The electrons are moving through this circuit. It's just these are balancing that movement in charge, becoming more and less negative by doing movements of its own through the salt bridge. The standard electrode potential is this. Calculate the electrode potential of the left-hand electrode in this. So they've told you need to figure out what this mysterious thing is in figure 2. So they've measured this initial voltage of 0.16. E cell is going to equal E reduced minus E ox. Reduced minus ox, right? They've told you the overall one is 0.16. And that equals, well, you can see this is Cu2 plus 2 minus the solid. That's being reduced. So that's going to be 0.34 minus whatever's been oxidized. So therefore, 0.16, so sorry, whoops, EOX is going to equal 0.34 minus 0.16. If we do that, we get 0.18. Cool. Plus 0.1. There you go. Both electrodes contain a strip of copper metal in a solution to this. State why the left hand does not have an electric potential of this. So if we look at the left hand electrode, it's saying why is it not got this perfect thing, even though we are, we've got Cu2 pluses here in copper. They've told you in this question that this side does not. What's the difference between the two? This and this. There's no other difference. So although you can remember that like it's going to be a standard electrode, blah, 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 I can already see that the only difference between the two of them is this versus this. And they've told that must, in this case, according to the question, lead to the change in that the electrode potential, which is obviously not this. And then in this case, what's happening is that the concentration is not 1 mole per decimeter cubed. There you go. So now it says give the conventional representation for this cell in figure 2 and include all state symbols. They've told you in this question that the Cu2 plus electrode is here, right? And that's going to be the one that's being reduced. So this one's got to be oxidized. So the one that's more negative goes on the left, which is your oxidizing one, and the one that's going to be reduced is on the right. However, we're switching between the two same ions, so the half cells are the actual half cells in this representation are the same. So here's your salt bridge. There's cell 1, whatever's going here and whatever's going here, and then there's cell 2, whatever's going here is whatever's going here. The oxidized forms of things go in the middle. So what I mean by that is we're switching between Cu2 plus aqueous and Cu solid, and the reduced bits go on the outside, like this. Because we're switching between copper and copper and copper and copper, it's all just, that's all it is. When the voltmeter is replaced by a bulb, the EMF of the cell decreases over time to 0, so just how the concentration of copper 2 ions in the left electrode changes the bulb when the bulb is lit. Give one reason why the EMF decreases to 0, and then the change in concentration on the left-hand side and why it decreases to 0. Fine. So E cell equals E reduced minus E ox, right? So if it's decreasing to 0, something's happening to the point where these are essentially being the same and they disappear. So suggest how these in the left-hand electrode changes when the bulb is lit. So if the bulb is lit, then, you've got, remember that this is your oxidation side. So we're going from Cu solid to Cu2 plus aqueous. So if that's the case, then the concentration has to increase, even if the circuit's running. Cu2 plus aqueous increases in its concentration because it's more of this is being oxidized to become those. However, why does the EMF decrease to 0? Over time, if the E cell is 0, then these must eventually just be equal and disappear and cancel each other out. So it must be that in both solutions, the Cu2 plus concentration in both solutions must be the same. Because if there's no, if there's no electrode left and this and that, blah, 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 then they're not going to, what's the word? They're not going to, actually have anything to reduce or oxidize with. So when anhydrous aluminum chloride reacts with water, Y is formed that contains a complex ion Z and chloride ions. So write down what you know in the question already that they've definitely told you. So you're reacting aluminium chloride, which is AlCl3, and we know we're reacting with water as well, so H2O. Don't know how many is yet, but I won't worry about that too much. We know that we've made chloride ions, Cl minus, and there's 3 of them, so I know there's going to be 3 Cl minus. And then it's saying you've got a complex ion of aluminium with Z. So it's a complex ion of aluminium with water in. The only thing I can think of, and you should be able to recognize, is H2O 6, 3 plus, and that. So then I need to have 6 H2Os there. There you go. Always write what the question's told you to start with, and then it's quite easy to do the rest. Now it says, give an equation to show how this can act as a Bronsted-Lowry acid. So when it's a Bronsted-Lowry acid, anything in the universe that's an acid puts out an H+, anything that is a base accepts an H+. So in this case, if it's showing you that this can act as an acid, already we could start by writing Al H2O 6, 3 plus, right? If it's acting as an acid, it's putting out an H+. So in this case, if it's adding an acid, something's got to accept it, and it's telling you with water. So we're going to add water. If it's acting as an acid, then that means that this water's gained the proton, because there has to be a base. Something's acting as an acid, something's acting as a base in these. Something has to take the proton. So if this H2O is acting as a base, it's going to be H3O plus aqueous, right? And then somewhere in here, we have lost a proton because it's acting as an acid. It's only from here. If H2O has lost an H+, what you got left behind is OH minus. So what happens is you end up with Al, H2O 5, OH, and then 2 plus because the charge has dropped by 1 aqueous. A lot of people think that that's a ligand substitution reaction. It's actually an acid-base reaction because one of these H2Os loses an H+, something else takes it like this, and you're left with that. There you go. So it's asking for two observations of this when you add it to solution Y. And solution Y, remember, is that the complex ion, right? The AlH2O6. Now, it's saying give two observations. So when you're adding, this is all to do with metal AQA ions. So things that form complex ions with metals, with water, sorry, that have 6 of them. A lot of them act as acids and bases, but the ones that are metal 3 pluses, what they'll do with a carbonate is that you'll make an OH precipitate. Whereas the 2 pluses will make MCO3, like a metal carbonate. And in this case, this is a 3 plus because we're doing aluminium. So I'm just going to write the equation first. I think that's the easiest way to do this. AlH2O 6 3 plus. We need to think what's it going to react with from the sodium carbonate because only want the ions, right? It's going to be the carbonate ions, which is CO3 2 minus. One of the products is that you're going to get an aluminium precipitate. So it's going to be AlH2O 3 OH with no charge. And that's aqueous. That's aqueous. That's solid. So generally, when you've got transition metals, metal ions, and all of this kind of stuff, if it's not charged, it's a solid. Plus something else. This has lost a proton. This will have accepted the proton because you can see it's going from H2O to OH, right? And if this has accepted a proton in H, then we're going to have to think of something that can, muck about and eventually make what it is. So when you add, generally, this is acting as an acid. This is a carbonate. An acid plus a carbonate makes a salt plus water plus carbon dioxide. So then we've got to balance it. Well, there's 3 protons lost from this, and 3 protons have been lost to give you 3 OH minuses, right? So that means we're going to have to have made, in order to make enough H2Os, because that's where the protons are going, we need to balance that. So there's 2 here, but then we've lost 3. So what I'm going to do is multiply that by 2, and then this is going to be times 2, which means we've now lost 6 H's, which eventually come here. So we're going to have 3 H2Os. If there's 3 H2Os, right, we need enough O's to go around for this, right? And we also need enough for this. So there's 3 here. Then if we put 3CO3 here, we've got, how many is that? That's 9. And if we have 3 H2Os, that's 3 O's, and then 3 CO2s, that's 6. So that's going to give you 6 plus 3, which is 9. So that adds up there. There you go. So then based on this, you can see what's the observation. Well, first of all, you make a white precipitate. And then as well as that, because you're making CO2 gas, you're actually seeing effervescence as well. Now it says aqueous potassium hydroxide is added into the solution Y, and then describe 2 observations that you would make, and then give an equation for what happens. So we're adding OH minuses, remember, and this is a metal aqua ion, meaning it can act as an acid, where it's giving away an H plus. So as you're adding it, what's happening is the AlH2O6. So if I just draw this now, AlH2O6 3 plus. What's happening is that as you're adding more and more OHs, this is giving away protons. It's giving a bit, it's giving a bit, it's giving a bit, it's giving a bit, until at one point you've given enough to form a precipitate. So what happens is you get AlH2O3 OH3 solid with no charge, aqueous. And we're adding OH minuses, right? This has lost 3 protons. This will have gained 3 protons. So we get 3H2 on this side as well, liquid. So the first thing is that you're going to make a white precipitate. But then as you're adding more and more and more OH minuses, there's going to be more and more protons lost. So eventually what happens is that you lose all of your H2Os because they've all lost their protons. So the reason that these 3 pluses do that is because they can polarize the H2Os here, making them weak. The bonds between these become weak, so you could drop off and break that off to give you an H plus. So in this case, eventually what happens is that the precipitate dissolves and you get a colorless solution. Because eventually, now what's happened is you've got AlH2O3 OH3, which is a solid, plus the 3 OH minuses, because now this is going to lose 3 more protons to give you Al OH6 3 minus plus H3H2O now. Alternatively, you can make AlOH4 minus as well, or you could go and just say only one of them have, but eventually it's just more proton loss. That's how I make sense of it, and there you go. So this question's about sodium and some of its compounds. Use your knowledge of structure and bonding to explain why sodium bromide has a higher melting point than that of sodium and higher of sodium iodide. So in that case, we need to describe what all of these are. So it says structure and bonding to explain why bromide has a higher melting point that is higher than that of sodium and higher than that of... Fine. So bromide is higher than sodium and also higher than sodium iodide. So we need to talk about each step one by one. So let's talk about structure. So Na, metallic bonding, which is where you've got positive metal ion attracted to a delocalized electron, giving a giant metallic lattice, right? For the ionic stuff, so NABR and NAI, this is an ionic lattice. So you have electrostatic attraction between oppositely charged ions, right? But that doesn't tell us why these are the way it is. It must be that these ionic bondings, the ionic bonds in NABR are stronger than the metallic bonds in Na and ionic in NaI, meaning more energy is needed to overcome them, right? But then that doesn't explain why the Br is stronger than the I. So NABR versus NaI, the only difference is you're really doing Br minus versus I minus. If you compare the two of them, the only difference between them, they're both group 7 or whatever, the only difference is that has more shells. Remember that this wants to take electrons from the Na, and this one does as well. If there's more shells, it's going to the outermost electrons. The outermost shell is further away from the nucleus, which means it's less strongly attracting those electrons. So what's happening is the NABR ionic bonding is stronger because I minus is bigger, and there's more shielding, so it attracts the electrons from Na plus in the ionic bond less, therefore less energy is needed to overcome, the bonds and so forth. That's all it is. So if you do it step by step like that, you'll never ever fumble it. It's telling you to talk about structure and then bonding. So structure is all of this stuff, which is here and here. Bonding is actually then talking about why these are, these differences are here, and then also you need to do a side-by-side comparison of one by each. Now it says when 250 milligrams of sodium was added to this water, a gas is produced. Give the equation and then calculate the volume of the gas. So the equation is going to make Na plus H2O gives you, it's going to make NaOH, and the rest is left behind because you only have one H and one S. It's going to be a half H2 than what's left, right? So then it says work out the volume of the gas that's produced. The gas that's made was hydrogen gas. So in that case, we're going to have to use PV equals nRT, and we want to work out V, which is going to be nRT and nRT over P, right? So list out what you know. So we know that R is 8.31, temperature is, 25, so we need to convert that to Kelvin. So that's going to be 298 Kelvin. What else do we know? We know that the pressure has to be in base units. You can't have kilopascals. It has to be 101,000. We can work. What we need to be able to do this, we need the moles of the gas that we're looking for, which is hydrogen. So we can work out the moles of the Na by doing its mass to 0.25. So it's 250 milligrams. So it's going to be 0.25 grams. Remember, because we're converting it over its MR, which is 23, which gives you 0.0109 moles. So therefore, the moles of H2 is going to be a half of that. So it's going to be 5.45 times 10 to the minus 3, So then V equals nRT over P. V is just going to be, 5.45 times 10 to the minus 3 times 8.31 times the temperature, 298, all over 101,000. If we do that, we get 1.336 times 10 to the minus 4 meters cubed, because this is all in base units, by the way. Now, the question wants it in centimeters cubed. So 1 meter is 100 centimeters. 1 meter squared is going to be, so what you've done to get from here to here is you've times by 100. So here to here, you're going to times by 100 squared. So that's going to be 100 with 2 more zeros, centimeters squared. So 1 meter cubed is going to be, well, you're going to times it by 100 cubes. It's going to be 1, 1, 2, 1, 2, 1, 2 centimeters cubed. So if we've got 336 times 10 to the minus 4 meters cubed, to get to centimeters is going to be times 10 with 6 zeros on it, so 10 to the 6, which is going to be, not 10 1 with 6 zeros on it, because 1, 2, 3, 4, 5, 6, right? So it's going to be 1.336 times 10 to the minus 4 times 10 to the 6, which gives you 133.6, which is roughly, we should match the number of significant figures in the question, this many centimeters cubed. Then it says calculate the concentration of moles per decimeter cubed in the sodium ion solution produced in this reaction. So what we need to do is we need to find out what the volume of this solution is and stuff. So here, what do we have? We have that much centimeter, that much water, right? So that's our volume. And how much sodium that. So we know that the moles of the sodium, and hence the moles of the sodium hydroxide, because you can see that 1 is 1 here, is going to be 0.0109 from before. So C equals N over V, which is going to be 0.0109 over its volume, which is 500 divided by 1,000 or times 10 to the minus 3, whichever one, which gives you 0.0217, which is roughly 0.022. Sodium also reacts with ammonium to form NaNH2 that has this NH2 minus ion. Draw the shape of this ion and include any electrons that influence the shape. So it's reacting with ammonia to form NaNH2, and it's got this ion, right? So NH3 is normally you've got a single bond, single bond, single bond, and then a lone pair, right? But they've told you in this question that it's got an NH2 minus ion in it. So what it's done is we've peeled off one of the H's. Remember that each one of these is a covalent bond. So there's a shared pair of electrons, one from nitrogen, one from the hydrogen. So if we've taken one of those away, then we've got one unbonded electron. But they've told you it's an NH2 minus ion, so we actually have another electron here that's negative. So that means we've got two lone, two bonding. So if that's the case, NHH and then, your lone pairs here, or your charge clouds in this case, which I'm going to draw like this, and then the brackets here, and then the minus. So we need to think about what bond angle it is. Well, it's 2 bonding, 2 lone, so it's going to be 104.5 degrees. So the justification, every single question that tells you why it's this shape, you've got to say this exact thing, is that, lone pair, I'm going to write LP for short, repel most. Then lone pair, bonding pair, BP I'm going to write. Then BP, BP, and I need to say why, because electrons repel apart as far as possible. So this question is about vanadium and its compounds and its ions, and then here's the, so it says here, identify the species that can be used to reduce VO2 to VO2 plus to VO2 plus, and in aqueous solutions and no further, and explain your answers. So we need to find whichever one is making it go in that direction, right? So we're going from VO2 with a 1 plus to VO2 with, VO with a 2 plus. So whichever one this is going to be whichever one falls in that direction. So let's see. So we're reducing it. So it's got to be, we're adding electrons to this. So that has to be on the left. So it's got to be here, right? Now, if we're going to reduce this one, we've got to pick something that oxidizes it and doesn't go any further. Something that gets oxidized. So the only thing that's going to be oxidized is what's more negative than this. So that's more negative than this. But then the problem is that you'll end up getting this. We don't want that. So that one's out. Now, this one is more positive. So, no, it's hideous how this table's been laid out. Why would you even do this? Then, this is more negative. It could work. This is also more negative, which could work. However, the problem is if we use Zn, right, then yes, you will make this, but then if you can see that this is here as well. So if you had Zn, then you'll have this, which is, more positive than that. So then this will get reduced into V3 plus. So it can't be that. It has to be Fe only. This table is hideously written out. Like, I just do not understand why you would do that, like, in this way. It's just pure, like, annoying. So the reagent we're going to use is we're going to use Fe2 plus, not 3 plus. They're asking you what your reagent is, what you're going to put into this. So we're starting with this. We're going to put this in. So we're going to add Fe2 plus. The reason is that it's E set, the E value for it of Fe2 plus is more negative than the VO plus with the VO2 plus. Therefore, it becomes reduced. Sorry, not reduced. It's oxidized to Fe3 plus. And, the VO plus 2 is reduced. Now it says give the oxidation state of vanadium in this thing here. So it's VO, H2O. So that's got overall nothing here. We know it's 2 plus, so we know that it's minus 2. So it's going to be something minus 2 gives you plus 2. It says before. So this ion exists as 2 isomers, one of them shown below. What's the other one? And state the type of isomerism. So H2O, H2O, Cl, Cl, H2O, H2O. So this is got to be cis-trans isomerism because you've got 2 different groups amongst 4 of them. So this is the cis one. The trans one is where they're on the opposites. So H2. Well, if I start actually by drawing the thing here with its things, like here, there, and then there, and then there, and then I can put them on opposite sides. So Cl, Cl, OH2, OH2, put our lone pairs there, H2O, and then H2O like that. There you go. Now it says heating this produces vanadium oxide, one other product given equation. So again, start by writing what you definitely know is going on here. So NH4VO3. If you heat it, you get vanadium 5 oxide. So vanadium 5 is going to be, 5 minus 2 is going to be V2O5 plus something else and water, right? So we know that we've definitely got this in the equation. So we've got V2O5, which is where the V comes from here. We've got H2O, which comes from a bit of here. And we're only heating this to make that. There's no other reagents in this. So what it's got to be left is got to be something that ends in NHs. It's probably going to be NH3, let's be real. So then what we do is we just look at what's in this and balance things out. So we've got V2O5 here, but we've only got 1 V here, so we need to put a 2 there. Now we've got 2 ends, but we've only got 1 there, so we're going to put a 2 here, right? So we've got 2 NH3 and all of that stuff. Now let's just check this all adds up. So we've got 2 NH4, 2 NH3, so that's 6 H's there. So we've got 2 H's left, so that's gone in here. Then if we look at the V's, we've got V2, V2, that's fine. And then 6 O's, 1 O here, 1 O here, so that's balanced. Done. Vanadium oxide is the catalyst used to make sulfur trioxide. Give 2 equations to show how the catalyst is used and regenerated. So vanadium 5, the trick here is that you only need to know the oxidation states of 5, 4, and so forth, right? It's only going down. You don't know any of that. 6. So if that's happening, then that means it's being reduced. So you've got V2O5, right, which is eventually becoming, it's going to have to be So the +5 to +4, right? So it's got to eventually be V2O4. Now, obviously, you should learn this as well. This is part of an equation that you do need to know, but you can kind of derive it like this. Now, they've told you that we're making sulfur trioxide here, so we're going to make SO3 as well. So if this is being reduced, this is being oxidized, right? So in this case, we're oxidizing this. That's -6 +6. We're going to have to, and this is losing 2 electrons. Then the other thing has got to be a +4 oxidation state. As in S has got to be a +4 oxidation state, which is going to be SO2 like that. Then, but this is a catalyst, which means we have to bring this back. So then we've got V2O4 must become V2O5 again somehow, right? That's just, you can, again, work with what you definitely know is going to happen, and you can put the gaps in. Between here and here, the only thing that I'm adding is an oxygen. So I'm just going to add a half O2. There you go. Now, the final lovely question. All of these types of questions, you need to, please, for the love of God, read it and then write a little flowchart or something just to make sense, because everyone looks at this and they work out moles blindly, don't know what they're doing, get no marks, and they're like, oh my God, why? This question's so hard, bro. I can't do it. Use your common sense and a bit of logic, right? So what I mean by that is literally make sense of what they did. They did this, they mixed it with this. Why did they do this step? Why did they do this? Why did they do that? What I mean by that is look at it line by line and make sense of what they've done. So 627 milligrams of this Na2 blah, 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 XH2O, right? What they did is they added 200 centimeters cubed, 0.250 an HCl of its volume and its concentration, sorry. Then, when they reacted, what they did is, after this was complete, they then made a mixture and added, and then it was made up to 250 centimeters cubed. Then what they did is they took 25 centimeters cubed of this, and then they titrated it. Don't say titrated, say they reacted with it. Know what you're actually doing and saying with, well, it says here, with this much aqueous sodium hydroxide. So we're adding NaOH, and we know that we're adding its concentration of 0.150. Then it says the mean titer was this. We know its volume is 26.60. It says calculate the value of X in the Na2CO3XH2. I show you working. The reason I say this, you need to figure out what's reacting with what the whole purpose of every single thing was. Here, they've added Na2CO3, which is a carbonate, to some acid, and then they made it up to 250, and then they added the NaOH. You need to think, what on earth is this reacting with here? If you look here and that's a lot of acid, and also if you worked it out, it'd probably be in excess as well. So it must be that this NaOH was to find out how much HCl was left. That's what must have reacted with it. That's the whole point of this, is if you know what's reacted with this, then you'll know exactly where to go. So then, what's happened is this has reacted with some of the HCl, and what's left behind will have reacted with this. So that means we can take the moles of this HCl, take this away from it, and whatever was left behind has to be what's reacted with the Na2CO3, right? So then the moles of the HCl is going to be its concentration times its volume, which is going to be 0.250 times 200 over 1,000. If we do that, we get 0.05 moles, right? Then we've also known that the moles of the NaOH in this titration is going to be its concentration times its volume, which is going to be 0.150 times 26.6 over 1,000. If you don't know what to do in this question, then obviously, yes, work out moles blindly, but you should be able to justify what you're going to do with every single step like I have just done there. Then you need to work out how many moles of this will have been needed to get there, right? This was how much you needed to do 25 centimeters cubed of this mysterious mixture with HCl. So the moles of NaOH needed for 250 is going to be your answer times 10, which is going to be that 3.99 times 10 to the minus 2, right? So then we know how much of this will have reacted with this in theory. We can then work out the excess left behind. So then the moles of the excess HCl is going to be your HCl one, which is 0.05 minus 3.99 times 10 to the minus 2, right? So if we do that, we end up getting 0.0101 moles. This is what was left. This is what's left when we've accounted for however much was here and here. That must mean that this is the moles of the HCl needed to react with that Na2 blah, 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 right? So then think about it logically in terms of what's happening now. So this HCl and the Na2 blah, 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 CO3, we're going to need 2 HCls for every one of these, because you need to quickly just think about an equation in this as well. So in this sense, the moles of the Na2 blah, 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 whatever, right, is going to be half of this, because that was how much was needed to neutralize it, 2-to-1 ratio, right? So then that means we're going to have 5.05 times 10 to the minus 3 moles. Then we now know the moles of this Na2CO blah, 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 and we also know its mass. So we can work out its MR by doing MR equals mass over moles, which is going to be, well, they told you in milligrams. We need to change it to grams. So 0.627 over 5.05 times 10 to the minus 3. If we do that, then we know that its MR is going to be, let's see what that gives us, 124.158, right? So then we know that this is the MR of the entire Na2CO3.xH2O. All we can do is just take this out, and whatever's left is how many H2Os we have. So 124.158 minus 2 lots of 23 minus 12 minus 3 lots of 16, which is just all of this, will give us, let's see, it gives you 18.15. Now the MR of H2O is just 18, so that means X has to be 1, because we only got one H2O. There you go. I hope that helped. Please like, share, and subscribe. You know the drill. I'm going to be adding more content soon, as well as papers like revision tips, what life is like at uni, all kinds of cool little stuff like that. So, stick around and see. Thank you very much. Take it easy.